About the Solar Dynamics Observatory in SOHO, and Jim has worked as a tool and die maker with a biology degree from the University of Chicago. He started in astronomy 12 years ago when he found a semi-functional 10-inch dot at a track, which I might hear about sometime. He joined Amateur Astronomers Inc., one of the largest astronomy clubs in New Jersey, and quickly became a technical committee chair. He led the club in the exoplanet observing team, and like Mario Mata, participated in the Celt Fun initiative, which stands for Filigree Extremely Little Telescope Follow-up Network. Which helps identify false positives and confirms transiting exoplanets. As a frequent visitor to Cape Ann, he found GAAC at a guerrilla astronomy event at Bearskin many years ago now, and has stayed in touch. Please welcome Jim Nordhausen.
Thank you very much for the lovely introduction. Sharing my screen by now. Good. So tonight we'll be talking about the Solar Dynamics Observatory, which has flown in space for quite a while, taking high resolution observations of the sun. But first, we're going to talk about its predecessor, SOHO.
Do a quick sound check, see if everybody can hear you.
Can everyone hear me online?
Okay.
I can hear him fine on Zoom.
Good. So NASA has a history of many long-lived missions, often outliving their expected mission times by several times over. Most notably, the Voyagers, which are still going strong. They just announced some kind of software fix where they're going to possibly extend the missions by another couple of years. Cassini, which was a very great mission around Saturn. They extended that a couple of times till the great demise when they crashed it into the planet, and Hubble, of course, Kepler, but SOHO and SDO are up there in the list too. SOHO especially when you hear the statistics. Now, brief introduction to SOHO. It's the Solar and Heliospheric Observatory. It was actually, it's in first Lagrange point L1, so it's kind of opposite where the James Webb Telescope is. It's on the inward side of Earth, Sun balance point there, while Webb is on the outside, past the Moon's orbit on the far side. So it says they're about 1.5 million kilometers away, and uninterrupted daylight. And it was launched in 1995. I don't know how I omitted putting it there. It's designed for a nominal mission lifetime of 2 years. It was extended a couple times and again, and we're now in 2023 and it's still operational. There's a few instruments that have had trouble and aren't performing well, but mostly still operational, which is incredible for a mission designed for 2 years. So they had a close call in 1998. Where they lost contact with the satellite completely. They actually had the help of Arecibo to find it. And then once they found out where it was, they were able to do some software bugs to help fix things. And then the gyroscope started failing. But what's amazing is they made it work without its gyroscopes, making it the first 3-axis stabilized spacecraft operating without gyroscopes. So it's groundbreaking for future designs. And it's still working. So it has 12 instruments which cover a large array of solar observations, more than SDO has, but the ones that complement and contrast are the EIT, which is Extreme Ultraviolet Imaging Telescope. That has direct counterpart on SDO, and it basically watches at 4 colors in the extreme ultraviolet. And these are the 4 wavelength bands from 171, 195, 294, and 304 angstroms. And I think they use the same color coding sequence on SDO when you'll see them later. Now, the 300 floor images, every time I look at them, they look very much like hydrogen alpha images because of the color. And the features are very similar, but this is nowhere near the visible band, and it's actually the helium-2 emission line they're looking at there. Okay, and the second instrument is LASCO, the large angle spectrometric coronagraph. You get some really interesting observations of coronal mass ejections with that, because it has a occulting disk on it. So it blocks the direct light of the sun. So it allows all the outer periphery stuff to become more visible. And
Jim,
yes,
sorry to interrupt, but what does LASCO stand for again?
let me go back. Large angle spectrometric coronagraph.
Sorry, what?
One more time. Stands for LASCO. Okay, and on with the show. So you'll notice on the center here, on the orange image on the left, you see this circle in the middle and a smaller circle on the blue image. That's actually the size of what the sun would be behind it. So the occulting disk is much larger and you see the information coming out of it. So as a little contrast of what they've the angles of view from the two different instruments. Well, this is a coronal mass ejection seen on the C3 LASCO image. You see a lot of like this heart-shaped thing on the top coming out of the periphery, and a lot of ejecta coming out in all different sides. But this is like a size comparison of the two. The orange one is the LASCO C2, and the blue one is the LASCO C3. So you get a lot more in close detail with the C2, and you can follow it on timelines as it expands outward into the C3 imagery. There's some very interesting software out there, like helioviewer.org is a website where you can go on and pull up images, past and present, from any one of a number of solar telescopes that NASA and ESA operate. Okay, next. So, and it's also used for a lot of comet finding. As you can see here in the image, there's a little sun grazing comet coming through. And there's a citizen science operation where they allow people to go in, examine the data, just so people can examine the data for these little objects. And to date, in 2020, they announced their 4,000th comet discovered. And as of 2 days ago on their website, 4,651 comets discovered so far by the Sun Tracer project. That's a lot of comets. So now we're going to get into the Solar Dynamics Observatory, which is the meat of the talk here. This was launched much later. It's already in its 13th mission year. So it's a nice boxy thing about the size of a small car. It's like 7 feet by 7 feet by about 13 feet. So it was launched in 2010. It was expected to last 5 years, but they gave it enough fuel for 10 years. I guess they saw how well SOHO was doing, so they figured let's give it a shot. But it's 13 years up and still performing admirably. None of the instruments have shut down. Oh, I see a little kitty watching the presentation. So it's heavy, 6,800 pounds, but a lot of it is fuel. 640 pounds of instrumentation, so they pack a lot in a small portion of the satellite weight. It's about the size of a small car, like I said, with wings. And it's in an orbit that's not it's not a geostationary orbit, but it's like geosynchronous. It's canted, so it always maintains communication with the White Sands base there, which is its head of operations. It always has to be kind of like line of sight to the receiving antennas for the amount of data that needs to be transferred. So orbit is in the radiation belt where they had to add a lot of extra shielding to it to protect the electronics, but since it's also affected by the space weather it's observing, it's kind of like an observatory into the degradation of its own electronics. So we'll see what happens over its lifespan. The disadvantage of being so high in orbit as opposed to other satellites is, costs more to get there. And they do have eclipses periodically. You'll see them sometimes in one of the videos I'll show later, doing a little jostling here and there, doing positioning moves as they're regaining, I think they're rotating or something, but I happened to catch accidentally a couple lunar eclipses. Well, one particularly in January 13th, 2021. I was just going over the data, like when I'm before work in the morning, if it's a cloudy day, just seeing what the sun is doing, because I'm an avid solar observer as well as a nighttime observer. So, so I happened to notice the moon just zooming through the field in a couple of the 48-hour videos. So I went frame by frame until I captured these two frames. Has 10 imaging instruments that with a 1 minute cadence between them. So each instrument takes photograph once every 10 minutes. So that's the difference in position from one instrument to the other during those that 10-minute cycle, and then boom, gone. Clip's done. And it turns out they actually announced it ahead of time. It was in their blog. So they have generated a tremendous amount of data over the first 9 years of operation, 350 million images in the archive, 3,000 science papers generated. There's a lot of institutions all around the world involved in the creation of all the instrumentation and in operations, because it's a joint project between the European Space Administration and NASA. So there's three main instrument packages: the HMI, the helioseismic magnetic imager, and I'm only going to say that once, the atmospheric imaging assembly, which gives you all the nice colored images, and the extreme ultraviolet variability experiment, which is a very important instrument, though it's not, the data is not very spectacular to look at. So this gives you a little bit of a size distribution of various instrument packages. The AIA is what does all the the far ultraviolet imaging in 10 different wavelengths. The HMI is that magnetic imaging pack, and the EVE is the extreme ultraviolet imaging system. Well, it's not really imaging, it's just gathering and integration of the output all at once. So the helioseismic magnetic imager is generating magnetograms, which cover the polarity of the magnetic fields on the sun. And this is basically what the magnetograms look like. You see positive and magnetic negative fields as white and dark spots. And they're often related with near and far sides of sunspots and other surface features. Some have spots, some not. But
Is this in a particular wavelength?
I don't know how this actually works. It's imaging the magnetic field,
Right.
not a particular wavelength of light. So I'm not really sure how it works.
Jim, as long as you're stopped, I have a serious question.
Yes.
350 million images. That's scary. What sort of metadata are we talking about? So you can find stuff.
You can scroll through, I mean, they have search features where you can go by date back to when the whole system started. You can call up like movies of the day in any of the various wavelengths,
Gotcha.
et cetera, et cetera. So, I mean, it's all freely available to the public. It's not like Hubble where all the data belongs to the team that requested it for 1 year and then it goes public, Oops, sorry, let's go back to that. So the magnetogram also generates intensity grams, which are essentially like white light views. That's the sunspots associated with this magnetogram. So you can see a lot of them are in similar locations. And in the lower left corner of every image, they have what the image is, the wavelength if applicable, the date and the time in UT. So every image is coded. So if you forget what it is, you can always look in the lower left corner if you didn't crop it out. So those intensity grams what you saw was the flat raw image before. So the one on the left here is they do a colorized version, and then they flatten it, which is eliminating what they call limb darkening effects on the outside, so that you can see the details more uniformly across the surface of the sun. So you can see that on the date, there were a lot of sunspot activity here. I believe this was from beginning of January when I first wrote this report for my other club. Okay, and the final HMI images generated are a Dopplergram, which basically shows where surfaces are moving towards and away from you. And all of these little pucker marks here, like here, here, and here, they're all related to the various sunspots. So that they look almost like little holes, like the surface is sinking in there where it's getting cooler. Okay, so this is the extreme ultraviolet variability experiment. Not much to look at, but it monitors the ultraviolet in, I think it's 28 different wavelengths or something like that, all corresponding to various emission lines of various atomic components. I don't think they ever launched an instrument quite like it. Like I said, it doesn't really produce pretty pictures. What it produces is data like this. It integrates all the light at that frequency coming off the sun into one total volume, and it goes over time. And you can see in the center bar here, all I did was click on this before I saved it, and these are just a small sampling of the 28 different the spectral lines available. You can see where the bar is. It's always slid halfway down. And some of them show a lot of variability. You can see this is a magnesium 9 line, and it's going up and down all over the place. This is a carbon-free emission line and 977 angstroms. That's very variable. And during the course of the day, you see it trending upward. Not sure what that means, but yeah, that's what they're trying to find out with all of this.
Excuse me, what's the time scale?
You can, this each is an hour. That's 11 o'clock, 12 o'clock, 13 o'clock. So, and the O3 emission line, it's almost flat as a pancake. In fact, a lot of them are very flat. It's hard to find ones that have a lot of variability. I was looking through them, trying to find some interesting data, but so it goes. Okay, so this is the main fun and games one, the atmospheric imaging assembly. So I'm not sure how they do it filtration wise, but they are able to do 10 different wavelengths through these 4 imaging assembly tubes here. I don't know if they have dichroic filters or something to split, but it's 10 different wavelengths. Oh, sorry, every 10 seconds. Okay, so it's, yeah, my mistake. I thought it was every minute. Okay, different cadence than I had mentioned earlier. I apologize for that. A lot of this is cut and paste right off of their website, so this is accurate information. So they color code all the data like they did on the SOHO data site there. And this is a little bit of the color coding. You can see the red again is the 304 angstroms. You have all the HMI magnetograms and stuff listed on here. And they also do a couple composite ones where they combine the data from several different wavelengths into some pretty interesting looking images that convey certain flare properties. And hey, here's visually what the 10 different wavelengths look like. Now 1600 and 1700 angstroms aren't far ultraviolet, but they have a lot of interesting detail. The 1700 angstrom one is very similar to the white light, but you notice you see a lot of like lighter colored areas around there where if you actually look at the sun through a Herschel wedge or some really high quality filters, you'll see brighter areas sometimes surrounding sunspots. That's what those areas are. And in the 1600 angstrom ones, you actually see like all the little fireworks going off around the sunspots as they're forming and being reabsorbed into the surface of the sun. Kind of a fun one to look at. And The 171 gives you a lot of flare data, but there's some on their website, there's some coding as what each one's supposed to represent. But here's the different image resolution. So this was on the left is the SOHO images, and it's, you know, nice image but a little fuzzy. In the middle you see stereo, which is a satellite I didn't bring up. They had 2 satellites that they launched going in opposite directions around the sun. So at a certain point in time, they're actually looking at the sun from both sides. I didn't want to pad the talk out too much, but the SDO imagery really kicked up the resolution a lot. So it's a lot more resolution and a lot more higher cadence than SOHO. Well, it's better instrumentation. So here's one of these 3 color images that are combined, and you'll see sort of around 4 o'clock here, there's actually an eruption going on here with the coronal mass ejection. And a lot of other data is visible. All the different spectral lines are looking at represent different color temperatures at a surface, going from the 304 angstrom at about 50,000 Kelvin up to 10 million Kelvin up here. So you see, it's basically each one's looking at different layers of the sun's atmosphere, and sometimes even below into the surface a little bit. And they also caught transits of Venus. This one happens to be in 171 angstrom channel. I'm sure if you go on their website, you can pull it up in any channel you like and play with the data. And they also combine the HMI data with the AIA data and come up with these lines that represent all the magnetic field lines going around from sunspot to sunspot. I'm amazed that they can do this, but computers are wonderful these days. And they even take difference images where you'll compare one image to the image previous to it. And what it does is anything that's different between the 2 images pops out. So here they recorded actual shock waves from a flare going off. So that this flare going off right here, it was sending off these shock wave ripples that you see in the right-hand image that were shooting off to the upper left, traveling at 2,000 kilometers a second, they pop. So there's a lot of interesting solar research being done here. Okay, so here's a little bit of what each of the wavelengths monitors. You see there's a lot of iron emission lines, which is basically the end of the line for fusion reactions. Once you fuse iron together, you can't use it any higher. So there's a lot of that in the outer corona. I don't know if the sun is blowing it off at all, but it's interesting that we're monitoring so much of that. Carbon 4 line is at 1600 angstrom one where it shows all the fireworks. And the 1700, like I say, is more of a continuum shot where it's similar to the white light. And here, as I said before, 304 angstroms corresponds to the helium-2 emission line. So here's a nice little movie of a little flare going off. So this is a 48-hour time-lapse movie. You can pull these up off of their site, like right up to the minute. I'll show you how that's done a little later when we go into operations. They're just doing a little positioning move there. That was a little frame change there. And you should see a little blowing off there, a little bit of an explosion. And in the next frame, we'll watch the same sequence of events in the 304 angstroms. So you'll see a little blow off before the one you saw in the previous video, as these little fireworks start to crackle at 6 o'clock. There shot off a little bit of a coronal mass ejection before the big blow off that's going to go now. Every wavelength captures flares a little differently. You see different features. This one you see a lot of the prominences in 304 angstroms, similar to how you see in hydrogen alpha. And this is a lovely video. Someone was capturing data by this. These black lines going across are measuring the velocity of the coronal rain falling back to the surface. So that's a big prominence loop with actually the material flowing up and then raining back onto the sun's surface. So why does all this matter? Well, there's a few things happen in our path, which is why we keep looking at the sun. So the SDO is the first satellite in the Living with a Star program, which NASA launched in 2010. There's been several satellites since then. Someone mentioned one that got really close to the sun. I was part of this program. I forget the name of the satellite.
Parker?
Yeah, that's one, the Parker program, yes. And I think there's a couple soon to be launched that are part of this program too. So they're trying to study the sun to effectively address a lot of different aspects of how space weather affects our planet. We want to send people up in space. There's a lot of radiation up there. We need to know how to deal with it. So they want to quantify how the sun actually works during its solar cycle between maxima and minima. That's a major project, what's going on inside the sun that generates the solar cycle. They want to understand the effects of how these disturbances may affect climate change. Also, like I said, with human space exploration, they want to find out how these particles affect humans and how to properly shield for them, and reliably protect electronic components. And actually, last one I kind of mentioned before, but so we hope to predict it, but that's obviously impossible. But at least we can get an early warning, perhaps, because a lot of these events you see, like I had a friend who's actually has a Daystar Quark, and he watched I think a couple of weeks ago there was a big aurora event. He watched 2 days earlier the big solar flare happen live while he was imaging, and then sure enough 2 days later aurora. So there's a couple of days warning at least, because it's not necessarily the light, it's all charged particles and they don't travel the speed of light. They have a finite velocity. So the major solar storms, the biggest one was the Carrington event in 1859. There was so much solar material ionic disturbance that it was actually charging up telegraph wires and electrocuting people who were operating telegraphs. Some of the wires were like burning up and melting off the poles and things. There was a lesser event that shut down New York City subways, and a few more that disrupt the power grids. The biggest problem now is our power grids are extremely susceptible because it induces the charge along the wires, and then they damage transformers, etc. I'm sure you're probably well aware of that, Bill. And so we'd like to get enough advance warning and try to make an event like that survivable again. So communications and utility companies have not been heeding the warning, so it's time to get more data and drill it into their skulls that we need to be ready for an event like this, or we're going to be in the Stone Age for a few months till we rebuild infrastructure. So let's go to the SDO site, and I'll show you how to pull up some of this nice fun data. This is their homepage. So if you go and click on this little button that says data up top, that will pull down this little menu. And if you go to the sun now, that'll call up the page where you can visit all the little different wavelengths of light available in far ultraviolet. And if you click on the data links button, it'll bring you this little menu. And these are different resolution values from low resolution to high resolution. The ones labeled PFSS have all those magnetic field lines traced on top of them. And at the bottom of most of them, they have a 48-hour video option where you can watch the previous 48-hour videos. Sometimes there's little pauses and gaps if they're missing some data here and there, or if the sun or Earth was passing in front, you'll see a little jumpiness. Yes.
We'll send out this URL on the listserv tonight, later after the meeting.
Sure. Sounds good. Yes, it's SDO. Yeah, at nasa.gov. You can pull up the missions and find it there. So on some of the data links, they don't have movies available, like the HMI intensity grams, because those are the ones they blend with the AIA images to generate those field lines. Okay, so here's a recent image that you can just call up a high resolution image. Oops, am I going backwards? No. Okay, what am I doing? Okay, this is where in the link for the Zoom meeting, I sent out a little thing for making a personal dashboard. So if you click on this link that says browse data dashboard, it'll come up with a screen that has 3 different images on it. But if you click on the little settings button up here, it'll bring down a thing where you can add or subtract all kinds of different images, including images that you can't get on the normal Sun Now image. Like you can actually get videos of the white light views that aren't available there. You can get high cadence images. Sometimes they have special projects where they take extremely high cadence images for a while that aren't available on the normal feed. You can add those on here. I think there's like 20 or 30 different versions of things you can put onto your own little things. So I clicked on this link and it appeared in the upper left-hand corner. So you can add up to 8 different things that if you have personal favorites you like to look at, you can add them to your own dashboard. You can move them around. And if you actually, if you hover on the bottom, though, there's like usually a link that pops up where you can enlarge them to full screen, and you can save them as videos, as MP4 files if you like something that you see. So that I added that to the dashboard. And if you want to get everything all arranged how you like it, if you click on this little link up here, a little window will pop up with a URL in it, and if you save this URL to your bookmarks, you can always call up your own personal dashboard arranged just the way you like it. So a few years ago, U.S. Postal Service honored the Solar Dynamic Observatory on its 10th anniversary with this collection of postal stamps. But I unfortunately was a little too late to get any, but I got the most recent ones. They put out the James Webb ones. So I'd like to thank the usual people who made all this data possible: Goddard Space Flight Center, the SDO websites, the SOHO websites, Lockheed Martin, University of California, Stanford, Amateur Astronomers Incorporated, my home club in New Jersey, and the usual fun people at GAAC here for all their support and encouragement. And thank you very much for your time and patience. Right. All right, do we have any questions for Jim online?
I have a question concerning the wavelength for the I saw this. I'm sorry, I got something running here.
Can you see something about
I got it. I'm sorry.
Already.
Yeah, the not coronagraph, the Dopplergrams. What's the frequency for the optimum Dopplergrams?
That's done with the magnetic intensity grams. So I don't know if there's a specific frequency involved with that. Those aren't ultraviolet images.
Okay, did you show any of those images, or is that, maybe I can get it on the website?
Well, I'll tell you what, I was gonna shut the presentation down and go live. So you can.
I pushed the wrong mouse and I started the other computer. It's like, uh-oh. It's dark in here.
One thing.
Here we go.
So a priest, an imam, and a rabbit.
There you go.
The rabbit says, hey, wait a minute, I think I'm a typo.
Ba-dum-bum.
Tip your waitresses.
Rabbit says. It's the right joke.
Sorry to give you a question that takes so much time.
That's all right.
I say hi.
Oh, there's a little kitty.
It's
That's a
Dory,
That's a calico.
long-haired calico,
Long hair.
full of mischief. Very cute.
I visited a friend. They had two black cats, one bigger
I
than the
love
other,
that. They're
brother
so
and sister.
gorgeous. My
Yeah,
grandmother liked black cats.
they kept bringing dead birds in.
They're gifts.
Yeah.
Current intensity gram for this very moment.
Oh, wow.
Oh, sorry, that's the Doppler gram.
Okay.
So
Actually, very cool.
And the left is rotating towards us and the right away.
I suppose. So we're trying to minimize this a little like most of it.
It's a counterclockwise kind of rotation there.
Pick it up.
I can't seem to minimize my screen here a little bit. All my controls are being blocked by the Zoom controls up top.
Say hi.
That's okay, Jim.
Oh, I can move them. Beautiful. Okay.
Can I get down?
So the left was coming towards us.
Puppy.
This is the data page where you can find all that. So that Dopplergram is all the way in the bottom here. So
Okay, excellent. Thank you very much. Great presentation. Thank you for all the info.
so let's see what's going on right now. This is the
It's blowing up.
so this is the last 48 hours currently.
It is magnificent.
There were a couple nice flares about a day and a half ago. I think well, people after missed this video. Have to go
Hey,
back.
Mike was Mario sending us solar images?
From time to time.
Just beautiful.
Such a wealth of data.
So this is the like view of the sun at the moment. The unflattened colorized view.
Looks pretty quiet.
Flashing areas were all involved with these sunspots around here, but there are actually a lot of areas that were flashing that were not involved with sunspots, which always fascinates me.
Where are we in the 11-year cycle now?
But we're getting in, we're at a solar minimum, which is always a good thing. So this is the 1600 angstroms where you get to see a lot of flashes and fireworks going on as the sunspots are forming and being reabsorbed.
Oh, I like that.
Yeah, that's one of my favorites.
Is this the carbon two?
No, this is, oh, yeah, I think it is. Yes, absolutely. You're right.
When it flashes bright, what is it doing?
It's emitting a lot more far ultraviolet light at 1600 angstroms.
Okay. Wasn't sure of the frequency.
Amazing.
That's what a flash of light means.
Put on that colorized spots too.
And the 1700 is kind of like white light, but with a lot more surface details. There's a lot of those flashes are sometimes happening in areas where there are no spots. So you can see all these active areas there as well, all the white areas.
What's the rotation of the sun period? A month?
It varies with latitude. I think it's like 28 days or something at the equator, and I think 30 something at the poles. But what I find fascinating as I've been observing the sun over a couple days, a couple of years, most of the sunspots always happen at like sort of mid latitudes.
It looks like.
They sort of match like where the north and south equatorial bands are on Jupiter. So I'm just wondering if just the mechanisms of the stirring up of the internal atmospheres are somehow similar but different.
Gorgeous.
Does the sun have a rotational axis angle or is it straight up and down?
Well, we're canted to its axis of rotation a little bit.
There is no straight up and down, I'm sorry to tell you.
Yeah, with reference to what?
Well, to the screen.
They have it up and down on the screen.
Sun's spin axis is pretty much the same as the Earth's orbital axis.
Oh, really? That's rare.
Okay, okay. So it's actually 0 compared to us.
Yes.
That's what I wanted to know.
All right, any more questions for Jim online?
Beside me.
Nope, just a thank you. Appreciate it.
Well, I think we ran quite a bit of time here, so that's good.
Okay, why don't you kill your share here?
I definitely
And we can see who we're talking to.
trying to find the button. There we go. No share.
All right.
There we go.
Jim, do you have any questions for Jim?
You don't have to. For Jim?
I'm sorry, I interrupted somebody.
I have a question for you right over
Yes.
here. Do you have any books you recommend on the Carrington event or any of the other?
None that I know of. I'm sure if you Google it, you'll find a lot of references available. But I mean, happened so long ago, there was even just a lot of newspaper articles written about it at the time.
Inducing a current in the ground and shutting down a subway, that's worth reading about too. What
Yes.
year was that? Do you remember?
It's in 1920, I believe.
Yes.
Is there any paleontological data that they've recovered from digging that reflects what the sun was doing a long time ago?
I am not sure. I couldn't answer that. I'm not gonna lie to you.
It's kind of an archaeological hard question. They can't even figure out what the dinosaurs were doing.
All right, we got another question in the room here.
Yes.
So you mentioned that the satellites help us understand the events, the aurora and the space weather.
Right.
In what way specifically? Which of the instruments warn us of a large amount of energy coming? Particles coming.
Well, through the wavelengths involving, all the photon emissions and various far ultraviolet and visible lights, you can physically see solar flares happening. When the coronal mass ejections happen, it's actually throwing pieces of the sun at us and they travel slower. So you get a visual warning that the other stuff is going to be coming in like 2 to 3 days. Does that answer your question?
All right. It's like
The Carrington event, there were astronomers actually watched the solar flares happen before it hit Earth.
So to be warned of space weather, we basically have to have people watching the sun 24/7.
Right, and especially in far ultraviolet wavelengths, they're all absorbed by the Earth's atmosphere. That's why it's all satellite observations. Those wavelengths don't even reach the Earth. They're all filtered by our atmosphere. And I believe you had a question?
I was kind of about the Carrington event, like, how did it happen? Why was that bigger than other events that happened?
It was just the biggest solar flare they ever observed. And I mean, before then, there were no telegraph grids or anything like that to really capture it and act as an antenna for it. So the more we build, the more that's susceptible, that's the bottom line.
Are these ions, hydrogen ions, helium? What ions are the bulk that show up here?
I think in the solar wind, there's a lot of protons and a lot of electrons too, I believe. Correct me if I'm wrong. And yeah, there's a full spectrum of particles that are emitted off the sun. I like the last one.
Fritz, I thought you asked a serious question. Oh, well.
Yes.
Well, that'll be the end of Bruce Willis, I think. Yes.
Have there been any ejections that have taken out any of these observatories for any period of time?
Not that I know of. I know a lot of times when there are solar events, they have to put satellites in safe mode so their electronics aren't adversely affected and things like that. Does affect GPS satellites, because all the geostationary satellites are out more higher in the radiation belts, so the low Earth orbit ones don't have to worry so much about it. They're below the Van Allen belts, et cetera. So,
Do we get gamma, X-ray, beta, and alpha waves at the speed of light?
Not usually.
sorry, what was that?
Do we get alpha, beta, gamma rays at the speed of light, like 8 minutes after they're launched? Do they show up here?
Gamma rays maybe, but alpha beta waves are charged particles. They're like nuclear components, and they probably have that's what's having the time lag.
Ah, okay, thanks.
Typically 1 million miles an hour. So it takes about 4 days to get here.
Okay, any other questions for Jim?
Hey.
All right, thank you, Jim.
Thank you very much, Jim. That was great.
Thank you. I really enjoyed this.
Well, people are still online. Let me say that for June, we have our own Phil Banks. You want to give them the 10-second, Tracy?
Sure. My presentation for June is called Race to Hit the Moon. Vern, Von Braun, and Kurland. These are the 3 principal people who were fascinated with and led the programs, one fictional, to actually do what had to come first, which was to design the launch vehicle, a projectile, and figure out all the mechanics to actually fire something at the moon and hit it. And that took place before the lunar landings. And actually the amount of new technology that was required for this phase outweighed what was left to go to get a man to the moon and back.
All right, thank you. That sounds really terrific. Look forward to it. All right, thank you, Jim. That was great. Thanks for coming up and being with us in person. Everybody, we're going to shut the door. It's good to see you too. I'll see you in June.
Take care,
All
gang.
right. Thank you again, everybody. Really appreciated this.
Bye.
Anecdotally, one of my Antarctic talks, you may have seen some photos of a friend of mine.
Night, Fritz.
Actually, does summer overs down in Antarctica, servicing space weather monitoring stations out on the glacier. He's spent 7 summers down there for New Jersey Institute of Technologies. Unfortunately, he had to, I think, lie on some of his medicals to get put down there. He's older than I am.
All right. All right, folks. Good night.
Good night,
Good
everybody.
night.
Thank you, Michael.
Thank you.